Hello everyone, welcome to Rasayan Academy, and today we are going to talk about the IR spectroscopy structure determination definitely, and this is our second video on it. So let's get started with the video. Alright, so before starting with the structure determination, I just want to remind you that I'm an educator on the Unacademy Plus platform and my name is Jagriti Sharma. And if you have not yet followed me, you can follow me for regular updates because guys, on the Unacademy we are having a discussion on a really lot of content, right? So these are our special classes which are basically free classes. These are free 1 hour sessions and we have talked a lot about the CSIR previous year questions in these special classes. So if you have not yet visited my profile, I would suggest you to visit it once to see what is the type of the content which is available over here. And definitely guys, there is a plus platform and the plus classes are a bit different. There are plus courses, so they are a bit different and they are definitely the paid versions of the same free 1 hour session that you are getting here. So in the plus course, basically we are trying to complete all the CSIR syllabus as well as trying to do as many practice questions as possible. Also before the exam, before the 2 months of the exam, we will be revising everything. So that is a paid platform and you are getting complete guidance for the CSIR exam from many educators like me. Okay, and guys, if you want to subscribe, then this is my code JAGRITI and it is going to give you a 10% discount on the subscription package. We are having different subscription package of 1 month, 3 months, 6 month and 12 month and 24 month. So if you are in college, let's say if you are in M.Sc, then you can plan for a 1 year subscription, or if let's say you are you just want to give the exam only preparing for the exam, then you can take the 6 month subscription as well. Completely depends on you. So I would suggest you to at least visit the website once because there is a lot of free content which is given by many educators like me. Okay. Alright guys, so now we are going to continue with the IR spectrum of alkenes. So we talked a bit about the alkane and alkene spectrum, the cis and trans alkene, how the how the cis and trans are going to how the dipole is changing the intensity of the peak. Okay, we talked about that. So here we are going to continue with the IR spectrum of alkenes, and there are a lot of factors that govern the spectrum of alkene. Okay, so the first thing is conjugation, right? So the first part is conjugation. How is conjugation affecting it? So conjugation decreases the force constant, weakens the carbon-carbon double bond, and hence shifts the peak to a lower frequency. Okay, so we definitely talked about this in the previous video, but now we are going to understand the concept with much more examples. Okay, so what I see is definitely this is our isolated alkene over here, 1643 centimeter inverse. It is isolated, just one carbon-carbon double bond. However, if I am taking, let's say, butadiene system, then automatically I see the frequency decreases. When I see styrene system, then again what happens is, because of the presence of phenyl group, against there will be a whole lot of conjugation structures for the styrene molecule over here, and definitely the the value also we can see has decreased from 1643 to 1630 for the styrene system for this carbon-carbon double bond. Okay, so this is how it is decreasing. However, let's say we are having a cyclic alkene, so we are having cyclohexene. So definitely guys, the value of cyclohexene is greater than for the aliphatic acyclic alkene, right? So the 6-membered ring is going to have a greater value as compared to a cyclic ring system. Also, if we are considering 5-membered ring, it is going to be greater than the 6-membered ring as well because of the greater ring strain. Right, so the ring strain also increases the frequency, it increases the force constant. Okay, alright, and what do we see now guys? See, what we see is over here, if we are having electron withdrawing system like this, if we are having a carbonyl, then definitely because of resonance into the carbonyl group, this alkene carbon-carbon double bond becomes very weak because of the electron withdrawing nature of the carbonyl group, and that is why we are getting such a low value. right? So even if we are comparing with styrene over here, we are still getting a much lower value, 16-17 centimeter inverse, right? So this value, see, this is the normal range, 1660 to 1600 centimeter inverse. So as we can see guys, that in the presence of a carbonyl group, the value has decreased to the lower end. Okay, so definitely multiple absorbances also may occur, may be observed due to conjugation. So basically there is one peak for the carbon-carbon double bond over here, but there can be multiple peaks also, because when there is when there is a resonance structure basically. So if I'm drawing the resonance structure like this of, let's say, 1,3-butadiene system, then it is also going to be like this. It is basically going to be like this. So here we can say we are having two alkenes, so we are going to get some peak for these two, but definitely we can also get a peak for this one because of the conjugation, because of the various resonance structures that we are having. Okay, so we can say that we can observe multiple absorption peaks for the alkene, conjugated alkene system. All right, okay, so now we are going to move forward and now we are going to see examples. Okay, so the example spectrum of trans 1,3-pentadiene system. So here we are having trans 1,3-pentadiene system. Okay, what do we observe over here? Definitely, first of all, we are going to focus on the left part of the spectrum and then we will go to the right hand side. Okay, so in the left part of this spectrum, what do we see is, we can see at again 3000, at the 3000 centimeter inverse value. So definitely the sp2 carbon stretch is carbon hydrogen stretch is going to be greater than 3000 over here on the left hand side, and the sp3 carbon hydrogen stretch is going to be lesser than 3000, which is for this methyl group. Okay, all right, now we are going to move forward and we are going to see the carbon-carbon double bond stretching frequency, which is at around, see, so we are getting two carbon-carbon peaks basically, because we are having two alkene double bond over here, so we are getting two sharp peaks, right? And the intensity is also good because it is having a good dipole moment over here. So it is 1620 and 1640 centimeter inverse. We are getting two peaks, right? So yes, again guys, and I would also like to show you the resonance structure as well, because we are getting two peaks for the conjugated system. Okay, so definitely this can be one of the explanations. And on the right hand side of the spectrum, all we can see are the bending vibrations. So here we can spot out, at around 1400 or let's say 1475, we can spot out the CH2 bending. Alright, and at 1375 we can spot out the 1375 or let's say 1350 centimeter inverse, we can spot the methyl bending vibrations, and so on. Definitely it is going to be a whole lot of bending vibrations over here. Alright, so basically we focused on how trans 1,3-pentadiene is giving us two peaks and the values are at around 1620 to 1640 centimeter inverse. Okay, so we are going to see now what is the effect of ring size. So first we saw the effect of conjugation. Secondly, we are going to see the effect of ring size or ring strain. Okay, so in the endo double bond, what is endo? The double bond is inside the ring. Alright, so guys, as we can spot out that I have written 4 to 5 systems over here. First is our this is cycloheptene, this is cyclohexene, cyclopentene and cyclobutene. Okay, so these are our systems over here, and as I can see, as I'm decreasing the size of the ring, the value of the endo double bond goes on decreasing. The frequency for carbon-carbon double bond, or the wave number with the carbon-carbon double bond, goes on decreasing with the ring size. Okay, alright. So it is least for the butane system, but as we are going to cyclopropene, definitely it is higher. As we can see, it is much higher as compared to the cycloheptene as well. So for the 3-membered ring system, it is going to be very high, and it is going to decrease till the 4-membered ring system. Okay, and why is that so? the wave number decreases with increasing ring strain till 90 degrees. Okay, so this is the specific value that we are having. Till 90 degree it is going to decrease. Okay, again it increases for cyclopropene. Okay, so if the angle has decreased below 90, it is again going to increase. And why does that happen? When the carbon-carbon double bond angle is greater than 90 degree, one of the carbon-carbon stretching vector coincides with the carbon-carbon stretching, and definitely there is an increase in the value. So basically the carbon-carbon single bond stretching vector combines with carbon-carbon double bond stretching. How can we see that? Okay, let's see guys. So see over here, only focus on the green part of the system. Only focus on the green part, because here I am showing you a carbon-carbon single bond, here it's a carbon-carbon double bond. Alright. So the carbon-carbon double bond is actually coinciding with this vector that I have written A. So this vector is collinear with the carbon-carbon double bond, and it is a vector which is come from the carbon-carbon single bond right over here. See, so this is our CC single bond, and it can be resolved into two vectors like this, A and B. Alright, and one of the vectors is collinear with carbon-carbon double bond stretching frequency, and that is why when the angle is less than 90 degree, when the angle is just a second. Alright, so when the angle is less than 90 degree, then it is increasing, then the value is going to increase. Right, so this is because of the vector calculation that we are able to say that below 90 degree it is going to increase, and above 120 degree. Right, and when the angle is above 120 degree, then again A is one of the vector is going to coincide with the carbon-carbon double bond. So here we can say that in both these possibilities, when the angle is greater than 120 degree, okay, which is in the case of cyclohexane, which is in the hexene, which is in the case of cycloheptene, right? So in this angle range also, the vectors are going to coincide and increase the value. Also, when it is below 90, again it is going to become collinear with the carbon-carbon double bond and is going to increase the value. So these are the two cases when it is greater than 120, which is in the case of the bigger ring systems, and when it is less than 90, which is in the case of cyclopropene system. Alright, so this is how the value is increasing for the carbon-carbon double bond. Alright, okay everyone, so I hope that this was a bit helpful for you to understand that why is the value decreasing from greater ring to a smaller ring only till butane system, and after butene it is again increasing. Okay, so I hope that you are able to understand this. Alright, so now what we are going to do is we are going to see the third effect, which is the substitution effect. So we have already studied about the conjugation effect, alright, and the the effect of ring size, and now we are going to see the substitution effect as well. So as we have already seen that as the size of the ring decreases basically in the endocyclic bond, then what happens? This is our largest ring over here, largest value, it decreases to cyclobutene system, and when the angle again goes less than 90 degree for cyclopropene system, it again increases. Alright, so these are our values. Now when we are having monosubstitution, when we are having monosubstitution on the carbon-carbon double bond carbon, basically alkene carbon, then what we can see is, guys, the value we are going to compare from this system as well as this system. So the value is definitely increasing. Okay, so if you are having monosubstitution, the value is increasing, and if you are having disubstitution, the value is increasing further. So if there is a substituent on the carbon-carbon double bond, then the value of the then the wave number is definitely going to increase. So in all these cases we can see 1611, 1650, 1679 for the 5-membered pentene system. For the 4-membered cyclobutene system, again 1566, it is 1641, 1675. Alright, and again for the cyclopropene system we can see 1656, 1788 and 1883 centimeter inverse. So guys, as we are increasing the substituent on the alkene carbon, definitely what is happening, definitely the value is increasing for the frequency as the force constant also increases. So what you have to do is, you don't have to remember all these values, this is just for reference, okay. You just have to remember that as we are, there are three groups, three effects that we have studied. The substitution, the conjugation effect decreases the value of the force constant but increases the intensity. In the second one we saw that the increase in or let's say the decrease in ring size is going to decrease the value only till the 4-membered ring, right? And now we have seen the substitution effect, that in whichever alkene system we are taking, it can be 6-membered, it can be 3-membered. So if we are putting the alkyl groups on the carbon-carbon double bond, then definitely it is going to increase the force constant value. So this is what you have to remember, okay. Alright guys, now we are going to talk about the fourth effect, which is the effect of ring strain on exocyclic carbon-carbon double bond. So previously in the last two slides we have talked about the endocyclic bond. Here we are talking about the exocyclic carbon-carbon double bond, okay. So see, if you are having an allene type of system, so if you are having an allene, right, so this is our allene, and what do we see is the carbon-carbon double bond stretching frequency is very high. It is even higher than our normal range of 1660, isn't it? This was our normal range, alright, for 1660 centimeter inverse. It is going much higher than that, 1940 centimeter inverse. Okay, now when we are starting from a 6-membered ring, we can see the value is under this range, 1660 to 1600 centimeter inverse, okay. And when we are decreasing the ring size, let's say we have the 6-membered ring over here, 1651 centimeter. When we are having 5-membered ring over here, this is again 1657 centimeter inverse. So 4-membered ring 1678, and 3-membered ring it is going to be 1780 centimeter inverse. So guys, as you can very easily see over here, the values are increasing with the decrease in the ring size. So here the frequency value is, basically if the ring size is increasing, we can say, let's say the ring size is increasing, the value is decreasing. So we can say it is inversely proportional to the ring size in the case of exocyclic double bond, and it was just the opposite in the case of endocyclic double bond, okay. So this is our free alkene system 1655, and here we are just showing the comparison, right? And this is because the S character increases for the exocyclic carbon-carbon double bond, okay. So the for the exocyclic carbon-carbon double bond, right, the S character increases as the ring becomes smaller, okay. So what happens is, as the S character increases in the carbon-carbon double bond, definitely the bond will try to become much more smaller, okay. So that is why the the frequency goes on increasing as the ring size decreases, okay. So usually these bonds that I have circled in green, these bonds which are basically the bonds on the carbon except the carbon-carbon double bond, so these bonds have more P character than the carbon-carbon double bond, okay. And that is why on decreasing the ring size, it increases further, right? So if we are decreasing the ring size further, let's say, then what happens, the P character on the bonds over here, these bonds increases, and the SS character increases for the carbon-carbon double bond, and that is why the frequency increases. So this was a much simpler explanation. We just have to remember that the as the ring size goes on decreasing over here, the S character in the carbon-carbon double bond increases, and hence the frequency, or let's say the wave number, increases with ring strain, okay. Much easier to remember. Alright, so guys, now we are going to talk about some important carbon-carbon stretching frequencies for acyclic alkene system. Okay, so firstly we are just going to talk about the vinyl system. Alright, so in the vinyl system, as we can see over here, that there is only I've just mentioned one R group, and the rest 3 are hydrogen basically. So the frequency is, let's say, approximately 1645 centimeter inverse. Alright. For the cis compound, for the cis alkene, we are having a higher frequency 1660 centimeter inverse, as well as the if we are looking for the same compound in trans, if you are looking for the same compound, same alkene system in trans, the value has increased, alright, basically, but the intensity of the peak has decreased, okay, because the dipole is basically cancelling out a bit much, right? So that is why the intensity has decreased. Okay, so yeah, so this is our vinylidene system that we are having over here, and in this system, on the same carbon, on the same alkene carbon, we are substituting 2 alkyl groups. And definitely guys, we had seen that on increasing the alkyl group substitution on the carbon-carbon double bond, definitely the value increases. So we started from 1645 centimeter inverse for the vinyl system, and here we are on vinylidene system with 1655 centimeter inverse. Definitely the value has increased. For cis we have seen, for trans we have seen. Okay, now we are going to go with the tri-substituted alkene system. So in the tri-substituted alkene system, we are only having one carbon hydrogen bond, and definitely guys, after increasing the alkyl groups on both the carbon, then what will happen? We started from vinyl 1 carbon 1645, 2 carbon 1655, 3 carbon it is 1675 to 1670, and this is what happens, right? So with increasing the tri-substituted, the value is found out to be this. For vinyl ether, if we are checking, right, for vinyl ether if we are checking, then we get the value to be around 1680 to 1660 centimeter inverse, and it is a strong peak. So here it is saying that it's a strong peak, right? So this is what we are having basically, and for the tetra substituted we are having this value 1665 to 1660 centimeter inverse. And guys, the value will decrease if we are having some conjugation. Alright, if we are having some conjugation, then the value is going to decrease, otherwise it is going to be greater than tri-substituted, right? It is going to be greater than tri-substituted, and with conjugation it decreases. Okay, alright. So now we are going to see some bending vibrations as well. So generally we are talking about some bending vibrations. If possible, you can if it is possible for you, then it's okay, you can try to remember some of them, but learning all of them is not necessary. So for the monosubstituted alkene system, here what we are having is, it is going to have monosubstituted alkyl group it has, and the bending vibrations are going to be on 1990 to 1910 centimeter inverse. Similarly, for cis 1,2 alkyl substituted alkene, we are having the bending vibration at 700. For trans, we are having the bending vibration at 970. For 1,1 disubstituted, which is basically our vinylidene system, here the value is 1890 centimeter inverse. For tri-substituted, it is 1815 centimeter inverse, and we are talking about CH bending, guys. Okay, we are talking about CH bending vibration of these systems over here. And when we are getting to tetra substituted alkene, then definitely there is no hydrogen, so there will be no bending vibration for carbon hydrogen, right, bond, right? Okay, and we are talking about the out of plane bending, and definitely guys, I've told you what are the bending vibrations. Definitely they are out of plane bending, out of plane bending vibrations they are. Okay, alright guys, so in this class also we had discussed a lot about the alkene system, about how the frequency of the alkene system can change with the changes in conjugation, ring sizes, exocyclic, endocyclic, double bond, and so on. So we have discussed a lot about the alkene ring system, the IR spectroscopy, and definitely guys, more knowledge is coming up in the next videos, in the following videos. If you liked it, then please subscribe to my channel, and please share it with your friends, and also give it a thumbs up. Thank you so much for watching guys. Definitely I'll see you in the next video, and if you want more free content, then you can visit me on the Unacademy website. Alright, thank you so much guys.